This problem from a Olympiad math competition asks us to find all pairs of positive integers, a and p, where p is prime, such that p to the power of a plus a to the power of 4 is a perfect square. We begin by expressing the condition as an equation. P to the a plus a to the fourth equals k squared for some positive integer k. To solve for a and p, a standard approach is to isolate a term to reveal algebraic structure. We will isolate the prime power term, p to the a. Subtracting a to the fourth from both sides yields this revised equation. The right-hand side has a specific structure. The term a to the fourth can be rewritten as the square of a squared. This substitution reveals a difference of two squares. Factoring the right side gives the product of k minus a squared and k plus a squared. This factorization is the key. Since k squared equals a to the fourth plus p to the a, we know k is greater than a squared, which ensures both factors are positive integers. The left side is a power of a single prime, p. Therefore, by the fundamental theorem of arithmetic, each factor on the right must also be a power of p. This allows us to set k minus a squared equal to p to the x and k plus a squared equal to p to the y for some non-negative integers x and y. As k and a are positive, k plus a squared is strictly greater than k minus a squared. Consequently, p to the I must be greater than p to the x, which implies y is strictly greater than x. Furthermore, since the product of p to the x and p to the y is p to the a, the sum of the exponents must be a. Thus, x plus y equals a. We now have a system of two equations. The next step is to eliminate the auxiliary variable k. To eliminate k, we can subtract the second equation from the first. This subtraction yields the following expression. On the left side, the k terms cancel, leaving 2 times a squared. On the right side, we can factor out the common term, which is p to the x. This manipulation results in a central equation that will govern our analysis. The problem now reduces to a case analysis based on the properties of p. We begin with the case where p is the only even prime, 2. Substituting p equals 2 into our central equation gives this result. Dividing both sides by 2 simplifies the equation. The two factors on the right side have a critical property. They are coprime. This is because the first factor is a power of 2, while the second is odd. Since their product is a perfect square, each factor must itself be a perfect square. This conclusion follows from prime factorization. The prime factorization of a squared must have all even exponents. Since the two factors are coprime, they share no primes. Therefore, for the combined factorization to have all even exponents, each factor's own prime factorization must consist of only even exponents, which is the definition of a perfect square. Let's focus on the odd factor. For 2 to some power minus 1 to be a perfect square, which we can call m squared, we can use modular arithmetic. If e minus x is at least 2, then 2 to that power is divisible by 4. This implies the expression is congruent to 3 modulo 4. However, no perfect square can be congruent to 3 modulo 4. This is a contradiction. Therefore, the only possibility is that u minus x equals 1. This simplifies the analysis considerably. With I minus x equal to 1, the odd factor becomes 1. This means a squared is simply equal to 2 to the power of x minus 1. Taking the square root, we find that a must be a power of 2. However, we also know a equals x plus I, which simplifies to 2x plus 1. This means a must be an odd number. Equating the two expressions for a leads to a contradiction. An integer cannot be both a power of 2 and odd unless it is 1. If the left side is 1, then x must be 1. But if x is 1, the right side is 3. This confirms there are no solutions for p equals 2. This parity contradiction can also be visualized. The yellow curve represents values of a that are powers of 2, while the red line represents values of a that are odd. They do not intersect at any integer, confirming that no solution exists. Next, we analyze the case where p is an odd prime. We return to our central equation. This case requires two subcases, one where p does not divide a and one where it does. Subcase 1. P does not divide a. This implies the exponent x must be 0. Substituting x equals 0 into our equation gives 2a squared equals p to the y minus 1. And since a equals x plus I, with x being 0, a is simply equal to I. Replacing I with a gives this final equation for the subcase. We test small integer values for a. If a equals 1, the equation becomes 2 times 1 squared equals p minus 1. This simplifies to 2 equals p minus 1. Adding 1 to both sides yields p equals 3. Since 3 is a prime, this is a valid solution. The first solution is the pair a equals 1, p equals 3. To verify, 3 to the first power plus 1 to the fourth is 4, which is 2 squared. The solution is correct. Next, we test a equals 2. The equation becomes 2 times 2 squared equals p squared minus 1. First, we evaluate 2 squared, which is 4. This simplifies to 8 equals p squared minus 1. Adding 1 to both sides gives 9 equals p squared. Taking the square root yields p equals 3, which is a prime. The second solution is the pair a equals 2, p equals 3. To verify, 3 squared plus 2 to the fourth is 9 plus 16, which equals 25, or 5 squared. The solution is correct. What about for a greater than or equal to 3? We must prove that no more solutions exist. Our goal is to show this equation has no solutions for any a greater than or equal to 3. Since AP is an odd prime, the smallest possible value for EP is 3. This gives us a useful lower bound for the right-hand side. P to the a minus 1 is always greater than or equal to 3 to the a minus 1. Therefore, if we can prove that 2a squared is always strictly less than 3 to the a minus 1, then our original equation can never hold. Let's check the base case. A equals 3. The left side is 18. The right side is 26. The inequality holds for our base case. A straightforward induction argument shows that the exponential right side grows much faster than the quadratic left side. The inequality holds for all a greater than or equal to 3. This means 2a squared can never be equal to p to the a minus 1 for these values of a. Consequently, no further solutions exist in this subcase. Subcase 2. P is an odd prime and divides a. We write a as p to the k times m, where p does not divide m and k is at least 1. Substituting this form of a into our central equation yields this result. Expanding the left side, we have 2m squared times p to the 2ak. We can determine x by comparing the p-adic valuation of both sides. The p-adic valuation of the right side is x because the second factor is not divisible by p. The p-adic valuation of the left side is 2k. Equating the valuations implies x must equal 2k. After canceling the powers of p, we are left with a new equation relating m and y. Let's rearrange this equation. We can express y in terms of our parameters by using y equals a minus x and substituting. Now, substitute this expression for I back into the rearranged equation. This simplifies to our final equation for this subcase. We now test values for p, k, and m. First, we test p equals 3. For k equals 1, the equation is 3 to the power of 3m minus 4 equals 2m squared plus 1. Testing m equals 2, we find a match as both sides equal 9. This corresponds to a equals 3 to the first power times 2, which is 6. The third solution is the pair a equals 6, p equals 3. To verify, 3 to the 6th plus 6 to the 4th equals 729 plus 1296, which is 2025, or 45 squared. The solution is correct. Next, for p equals 3 and k equals 2, the equation becomes 3 to the power of 9, m minus 8 equals 2m squared plus 1. Testing m equals 1 gives another match, as both sides equal 3. This corresponds to a being 3 squared times 1, which is 9. The fourth solution is the pair a equals 9, p equals 3. To verify, 3 to the 9th plus 9 to the 4th is 26,244, which is 162 squared. The solution is correct. We must now prove that no other solutions exist. This requires a bounding argument. We return to our final equation from this subcase. We will show that for larger values, the left side grows far too rapidly to ever equal the right side. First, let's analyze the case where p is a prime greater than or equal to 5. Let's test the smallest possible values. K equals 1, m equals 1, and p equals 5. Substituting these values into our equation gives this. This simplifies to 5 equals 3, a clear contradiction. For any larger values of p, k, or m, the exponential left side will be even larger. Therefore, no solutions exist for p greater than or equal to 5. Now let's return to p equals 3 and prove there are no solutions for k greater than or equal to 3. This is our equation for p equals 3. We examine the smallest possible case, k equals 3 and m equals 1. The left side becomes 3 to the power of 15. The right side is simply 3. 3 to the 15th is over 14 million. This is vastly larger than 3. For any larger k or m, the disparity only increases. No solutions exist for a k greater than or equal to 3. This rigorous analysis confirms that the only solutions from this subcase are the two we found. Having completed the case analysis, we can summarize the complete set of solutions. There are exactly 4 pairs, A, P, that satisfy the given condition. It is noteworthy that every solution involves the prime P equals 3. This problem illustrates a common theme in number theory. A general question about all primes can sometimes reduce to a specific and often surprising result for a single prime. Thank you for joining us for this problem. If you found this analysis interesting, please consider subscribing for more content.